Hi, we are going to start a new set of videos in which we are going to design and simulate a buck converter like this one. It's a topology that we have already studied in previous videos under ideal conditions. So now we are going to design this converter using a simulation software that is called LTspice. This software is very popular for two reasons. The first one is that it's free, so everyone can use this simulation software, and the second one is that many of the power electronics manufacturers provide simulation models of the devices they manufacture for this software. So in this way, if you want to choose or if you want to evaluate what happens if you use a particular MOSFET like this one, you can download the simulation model of the manufacturer, put that model in your simulation circuit, and check the results you obtain. So in this way you can obtain, let's say, results that are similar to the ones that you obtain in a real prototype. Well, here we have the specifications we are going to consider for the buck converter design. The input voltage is 12, output voltage 3.3. We are going to consider that the output power is 50 watts, so the output current is 15.15. The peak-to-peak current ripple through the inductor is 3.03 amps. The peak-to-peak, or the output voltage ripple of the design must be equal or lower than 16.5 millivolts. And this is not a specification, it's something that we have to choose in the design process, is the switching frequency. So initially we are going to start with a very popular value, 100 kilohertz, and as we progress in the design process, optimizing perhaps efficiency or size, we are going to modify this value. Well, and I want to introduce a possible application in which we can find similar specifications to those that we are considering here, and that application is the supply of a microprocessor in which 3.3 volts is a very common supply voltage. So in that case, typically we obtain the power from the grid, we rectify the sinusoidal voltage, we obtain a constant value, and then we reduce that voltage to 12 volts. Okay, that is the input of our converter. Then our buck converter is going to supply the microprocessor with 3.3. But in a general way, we can also consider that those 12 volts come from a battery. Okay, it's a general example. Well, let's see the objectives of this project. First of all, we want to validate the analysis that we have performed in previous videos where we consider ideal conditions. Then we want to see how we choose the components for a real buck converter. We also want to evaluate the impact of the parasitic elements of real devices. Okay, it's not real devices. We are going to consider the parasitic elements of the simulation models provided by the manufacturers, but the conclusions will be the same. Okay? And moreover, this project will allow us to introduce some techniques that we can use in the design process to increase the efficiency or to reduce the size of the converter. Well, some final comments. This is a simple project. Okay, people who already know or who already have experience with power electronics will not find anything useful probably in this video. Okay, so this is the scope of this project is for people who start working with power electronics. So in this way we are going to simplify the explanations, we are going to provide intuitive explanations. Moreover, another important point, we are going to consider only the power stage design of the converter. We are not going to talk about the control part of the converter. And moreover, although we are going to use the simulation models of the manufacturers, it's important to note that the accuracy is not 100% perfect. So the message is, what we are going to consider, or what is important from about the results we are going to get, is the increase or decrease of the parameters, not the specific value that we obtain. For instance, if we increase the switching frequency, the conclusion that we are going to get is that switching losses rises, but the specific value, the specific increase that we will see in simulation is not important, because the simulation models are not perfect. Okay, so in this way we will see a lot of trade-offs that we have to solve, or we have to alleviate as we progress in the design of a converter. So with this, we finish with the introduction of the project, and in the next video we are going to start with the design itself. So see you